Friends, today I am discussing about the most important chapter of science class 9th, from which minimum 2 to 3 questions are asked in every exam, so it is most important. So let's start without wasting of time. Chapter 1, Matter in our surroundings. As we look at our surroundings, we see a large variety of things with different shapes, size, and textures. Everything in this universe is made up of material, which scientists have named matter. The air we breathe, the food we eat, stone, clouds, stars, plants, and animals, even a small drop of water or a particle of sand, everything is matter. Everything in this universe is made up of material, which scientists have named matter. The air we breathe, the food we eat, stones, clouds, stars, plants, and animals, even a small drop of water or a particle of sand, everything is matter. We can also see as we look around that all the things mentioned above occupy space and have mass. In other words, they have both mass and volume. What? They have both mass and volume. Okay. Since early times, human beings have been trying to understand their surroundings. Early Indian philosophy classified matter in the form of 5 basic elements: the Panch Tattva, air, earth, fire, sky, and water. Early Indian philosophers classified matter in the form of 5 basic elements: the Panch Tattva, air, earth, fire, sky, and water. According to them, everything living or non-living was made up of these 5 basic elements. Ancient Greek philosophers had arrived at a similar classification of matter. Okay. Modern day scientists have evolved two types of classification of matter based on their physical properties and chemical nature. Yes. In this chapter, we shall learn about matter based on its physical properties. Chemical aspects of matter will be taken up in subsequent chapters. Yes. Next, physical nature of matter. Matter is made up of particles. For a long time, two schools of thoughts prevailed regarding the nature of matter. One school believed matter to be continuous like a block of wood, whereas the other thought that matter was made up of particles like sand. Let us perform an activity to decide about the nature of matter. Is it continuous or particular? Activity: take a 100 ml beaker, fill half the beaker with water and mark the level of water. Dissolve some salt या sugar with the help of a glass rod. Okay. Observe any change in water level. What do you think has happened to the salt? Where does it disappear? Does the level of water change? Okay. In order to answer these questions, we need to use the idea that matter is made up of particles. What was there in the spoon, salt or sugar, has no spread throughout water. This is illustrated in figure 1.1. Here, 3 beaker. First foremost, Particles of water magnified millions of times. Water add salt by spoon. Water stirred salt by glass rod. Then water salt mixed. When we dissolve salt in water, the particles of salt get into the spaces between particles of water. How small are these particles of matter? Activity 1.2. Take 2 to 3 crystals of potassium permanganate and dissolve them in 100 ml of water. The SI unit of mass is kilogram, kg. The SI unit of volume is cubic meter. The common unit of measuring volume is liter. Okay, such that 1 liter बराबर 1 dmq. 1 liter बराबर 1000 ml. 1 ml बराबर 1 centimeter cube. Take out approximately 10 ml of this solution and put it into 90 ml of clear water. Next, take out 10 ml of this solution and put it into another 90 ml of clear water. Okay. Next, keep diluting the solution like this 5 to 8 times. Is the water still colored? Here is 5 beaker. In this beaker 100 ml of solution and experiment. Estimating how small are the particles of matter with every dilution through the color becomes light, it is still visible. Okay. This experiment shows that just a few crystals of potassium permanganate can color a large volume of water, about 1000 liter. So we conclude that there must be millions of tiny particles in just one crystal of potassium permanganate, which keep on dividing themselves into smaller and smaller particles. The same activity can be done using 2 ml of Dettol instead of potassium permanganate. The smell can be detected even on repeated dilution. Okay. Here, important facts. The particles of matter are very small. They are small beyond our imagination. Got it? Characteristics of particles of matter. Next, particles of matter have a space between them. In activity 1.1 and 1.2, we saw that particles of sugar, salt, Dettol, or potassium permanganate got evenly distributed in water. Similarly, when we make tea, coffee, or lemonade, nimbu pani, particles of one type of matter get into the spaces between particles of the other. This shows that there is enough space between particles of matter. Okay. Particles of sugar, salt, Dettol, or potassium permanganate got evenly distributed in water. Yes. Similarly, when we make tea, coffee, or lemonade, nimbu pani, particles of one type of matter get into the spaces between particles of the other. This shows that there is enough space between particles of matter are continuously moving. Activity Put an unlit incense stick in a corner of your classes. How close do you have to go near it so as to get its smell? Okay. No, light the incense stick. What happens? Do you get the smell sitting at a distance? Record your observation. Activity 1.4. Take 2 glasses beakers filled with water. Put a drop of blue or red ink slowly and carefully along the sides of the first beaker and honey in the same way the second beaker. Next, leave them undisturbed in your house or in a corner of the class. Record your observation. Next, what do you observe immediately after adding the ink drop? What do you observe immediately after adding a drop of honey? Next, how many hours or days does it take for the color of ink to spread evenly throughout the water? Activity 1.5. Drop a crystal of copper sulfate or potassium permanganate into a glass of hot water and another containing cold water. Do not stir the solution. Allow the crystals to settle at the bottom. What do you observe just above the solid crystals in the glass? Next, what happens as time passes? What does this suggest about the particles of solid and liquid? Does the rate of mixing change with temperature? Why and how? From the 3 activities 1.3 and 1.4 and 1.5, we can conclude the following. Particles of matter are continuously moving, that is, they possess what we call the kinetic energy. Particles of matter are continuously moving, that is, they possess what we call the kinetic energy. As the temperature rises, particles move faster. Yes. So we can say that with increase in temperature, the kinetic energy of the particles also increases. We can say that with increase in temperature, the kinetic energy of the particles also increases. Okay. In the above 3 activities, we observe that particles of a matter intermix on their own with each other. They do so by getting into the spaces between the particles. Okay. This intermixing of particles of 2 different types of matter on their own is called diffusion. This intermixing of particles of 2 different types of matter on their own is called diffusion. Okay. We also observe that on heating, diffusion becomes faster. We also observe that on heating, diffusion becomes faster. Why does this happen? Okay, let's see. Particles of matter attract each other. Activity 1.6. Play this game in the field. Make 4 groups and form human chain as suggested. Next, the first group should hold each other from the back and lock arms like IDU Missimi dancers, just like figure 1.3. The second group should hold hands to form a human chain. The third group should form a chain by touching each other with only their fingers. Now, the fourth group of students should run around and try to break the three human chains one by one into as many small groups as possible. Which group was the easiest to break and why? If we consider each student as a particle of matter, then in which group the particles held each other with the maximum forces? Yes. Activity: take an iron nail, a piece of chalk and a rubber band. Try breaking them by hammering, cutting or stretching. Yes. In which of the above three substances do you think the particles are held together with greater force? Yes. Activity: take some water in a container. Try cutting the surface of the water with your fingers. Okay. Were you able to cut the surface of water? What could be the region behind the surface of water remaining together? Yes. The above three activities 1.6, 1.7 and 1.8 suggest that particles of matter have force acting between them. Yes. These force keep the particles together. Yes. The strength of this force of attraction varies from one kind of matter to another. Okay. States of matter. Observe different types of matter around you. What are its different states? We can see that matter around us exists in three different states: solid, liquid and gases. We can see that matter around us exists in three different states: solid, liquid and gas. These states of matter arise due to the variation in the characteristics of the particles of matter. Yes. Now, let us study about the properties of these three states of matter in detail. First activity: the solid state. Activity: collect the following articles: a pen, a book, a needle and a piece of wooden stick. Yes. Sketch the shape of the above articles in your notebook by moving a pencil around them. Yes. Do all these have a definite shape, distinct boundaries and a fixed volume? What happens if they are hammered, pulled or dropped? Are these capable of diffusing into each other? Try compressing them by applying force. Are you able to compress them? Okay. All the above are examples of solids. We can observe that all these have a definite shape, distinct boundaries and fixed volumes. That is, have negligible compressibility. Solids have a tendency to maintain their shape when subjected to outside force. Yes. Solid may break under force, but it is difficult to change their shape, so they are rigid. Consider the following. A. What about a rubber band? Can it change its shape on stretching? Is it a solid? B. What about sugar and salt? when kept in different jars, these take the shape of the jar. Are they solid? See. What about a sponge? It is a solid, yet we are able to compress it. Why? Okay. All the above are solids as. Yes. Of course. A rubber band changes shape under force and regains the same shape when the force is removed. If excessive force is applied, it breaks. The shape of each individual sugar or salt crystals remains fixed. Whether we take it in our hand, put it in a plate or in a jar. Yes. A sponge has minute holes in which air is trapped. When we press it, the air is expelled out and we are able to compress it. Yes, of course. Next, the liquid state activity. Collect the following: A. Water, cooking oil, milk, juice, a cold drink. B. Containers of different shapes. Put a 50 ml mark on these containers using a measuring cylinder from the laboratory. Of course. What will happen if these liquids are spilled on the floor? Okay. Measure 50 ml of any one liquid and transfer it into different containers one by one. Does the volume remain same? Yes, of course. Does the shape of the liquid remain the same? Of course. When you pour the liquid from one container into another, does it flow easily? Of course. We observe that liquid have no fixed shape but have a fixed volume. Here we observe that liquid have no fixed shape but have a fixed volume. They take up the shape of the container in which they are kept. Liquids flow and change shape, so they are not rigid but can be called fluid. Liquids flow and change shape, so they are not rigid but can be called fluid. Yes. Refer to activities 1.4 and 1.5, where we saw that solid and liquids can diffuse into liquids. Yes. The gases from the atmosphere diffuse and dissolve in water. These gases, especially oxygen and carbon dioxide, are essential for the survival of aquatic animals and plants. The gases from the atmosphere diffuse and dissolve in water. Yes. These gases, especially oxygen and carbon dioxide, are essential for the survival of aquatic animals and plants. All living creatures need to breathe for survival. The aquatic animals can breathe underwater due to the presence of dissolved oxygen in water. The aquatic animals can breathe underwater due to the presence of dissolved oxygen in water. Thus, we may conclude that solid, liquid, and gases can diffuse into liquids. The rate of diffusion of liquid higher than that of solids. This is due to the fact that in the liquid state, particles move freely and have greater space between each other as compared to particles in the solid state, of course. Next, the gaseous state. Have you ever observed a balloon seller filling a large number of balloons from a single cylinder of gas? Yes. Inquiry from him how many balloons is he able to fill from one cylinder. Ask him which gas does he have in the cylinder. Here some activity. Take 300 ml syringe and close their nozzles by rubber cork as shown in figure 1.4. Remove the piston from all the syringes, leaving one syringe untouched. Fill water in the second and pieces of chalk in the third. Insert the piston back into the syringe. You may apply some Vaseline on the piston before inserting them into the syringe for their smooth movement. Now, try to compress the content by pushing the piston in each springs. Here, gas rubber cork of a spring. What do you observe? In which case was the piston easily pushed in? Next. Question is, what do you infer from your observation? Let's see. We have observed that gases are highly compressible as compared to solid and liquids. Yes. The liquefied petroleum gas LPG cylinder that we get in our home for cooking or the oxygen supplied to hospitals in the cylinders is compressed gas. Compressed natural gas is used as a fuel these days in vehicles. Due to its high compressibility, large volumes of a gas can be compressed into a small cylinder and transported easily. The liquefied petroleum gas LPG cylinder that we get in our home for cooking or the oxygen supplied to hospitals in cylinder is compressed gas. Compressed natural gas is used as a fuel these days in vehicles. Due to its high compressibility, large volumes of a gas can be compressed into a small cylinder and transported easily. Okay, we come to know what is being cooked in the kitchen without even entering there. By the smell that reaches our nostrils. How does this smell reach us? The particles of the aroma of food mix with the particles of air spread from the kitchen reach us and even further away. Okay. The smell of hot cooked food reaches us in seconds. Compare this with the rate of diffusion of solids and liquids. The smell of hot cooked food reaches us in seconds. Compare this with the rate of diffusion of solids and liquids. Okay. Due to high speed of particles and large space between them, gases show the property of diffusing very fast into other gases. In the gaseous state. The particles move about randomly at high speed. Due to this random movement, the particles hit each other and also the walls of the container. The pressure exerted by the gas is because of this force exerted by a gas particles per unit area on the walls of the container. Here ABC show the magnified schematic picture of the three states of matter. The motion of the particles can be seen and compared in the three states of matter. Here A is solid, B is liquid, and C is a gas. Can matter change its state? We all know from our observation that water can exist in three states of matter: solid as ice, liquid as the familiar water, and gas as a water vapor. What happens inside the matter during this change of state? What happens to the particles of matter during the change of states? How does this change of state take place? We need answer to this question, is not it? Effect of change of temperature. Here is activity 1.12. Take about 150 gram of ice in a beaker and suspend a laboratory thermometer so that its bulb is in contact with the ice, as in figure 1.6. Here is a figure. Iron stand here, thermometer, glass stair, beaker is a in beaker ice cube, in below in A image burner. Similarly in B thermometer, iron stand, glass stair, beaker. In B beaker have a water, and in bottom burner. Figure 1.6, a conversion of ice to water, and B conversion of water to water vapor. Start heating the beaker on a low flame. Note the temperature when the ice starts melting. Okay. Note the temperature when all the ice has converted into water. Next, record your observation for this conversion of solid to liquid state. Next, no. Put a glass rod in the beaker and heat while stirring till the water starts boiling. Okay. Keep a careful eye on the thermometer, reading till most of the water has vaporized. Record your observations for the conversion of water in the liquid state to the gaseous state. Okay. On increasing the temperature of solids, the kinetic energy of the particles increases. Due to the increase in kinetic energy, the particles start vibrating with greater speed. On increasing the temperature of solids, the kinetic energy of the particles increases. Due to the increase in kinetic energy. The particles start vibrating with greater speed. Okay. The energy supplied by heat overcomes the forces of attraction between the particles. The particles have their fixed position and start moving more freely. A stage is reached when the solid melts and is converted to a liquid. Okay. The minimum temperature at which a solid melts to become a liquid at the atmospheric pressure is called its melting point. The minimum temperature at which a solid melts to become a liquid at the atmospheric pressure is called its melting point. Yes, got it? The melting point of a solid is an indication of the strength of the force of attraction between its particles. Yes, got it? The melting point of ice is 273.15 Kelvin. It is most important question, so mind it. The process of melting, that is change of solid state into liquid state, is known as fusion. The melting point of ice is 273.15 Kelvin, and the process of melting, that is change of solid state into liquid state, is also known as fusion. Okay. When a solid melts, its temperature remains the same. So, where does the heat energy go? You must have observed during the experiment of melting that the temperature of the system does not change after the melting point is reached till all the ice melts. This happens even though we continue to heat the beaker, that is, we continue to supply heat. This heat gets used up in changing the state by overcoming the forces of attraction between the particles. As this heat energy is absorbed by ice without showing any rise in temperature, it is considered that it gets hidden into the contents of the beaker and is known as latent heat. As this heat energy is absorbed by ice without showing any rise in temperature, it is considered that it gets hidden into the contents of the beaker and is known as the latent heat. The word latent means hidden. The amount of heat energy that is required to change 1 kg of a solid into liquid at atmospheric pressure at its melting point is known as the latent heat of fusion. The amount of heat energy that is required to change 1 kg of a solid into liquid at atmospheric pressure as its melting point is known as the latent of heat of fusion. So, particles in water at 0 degree Celsius to 73 Kelvin have more energy as compared to particles of ice at the same temperature. So, particles in water at 0 degree Celsius to 73 Kelvin have more energy as compared to particles in ice at the same temperature. Okay. When we supply heat energy to water, particles start moving even faster At a certain temperature, a point is reached when the particles have enough energy to break free from the force of attraction of each other. At this temperature, the liquid starts changing into gas. Okay. The temperature at which a liquid starts boiling at the atmospheric pressure is known as its boiling point. Boiling is a bulk phenomena. The temperature at which a liquid starts boiling at the atmospheric pressure is known as its boiling point. Boiling is a bulk phenomena. Okay. Particles from the bulk of the liquid gain enough energy to change into the vapor state. For water, this temperature is 373 Kelvin, 100 degrees Celsius equal to 273 plus 100 equal to 373 Kelvin. Okay. Can you define the latent heat of vaporization? Question is, can you define the latent heat of vaporization? Do it in the same way as we have defined the latent heat of fusion. Okay. Particles in steam, that is water vapor at 373 Kelvin or 100 degrees Celsius have more energy than water at the same temperature. This is because particles in steam have absorbed extra energy in the form of latent heat of vaporization. Here some facts. It is most important. When solid in given heat, then convert it into liquid state, and when liquid in given heat, then it is converted into gaseous state. Similarly, when gases is cooled, then it convert into liquid state, and liquid is cooled, it convert into solid state. So we infer that the state of matter can be changed into another state by changing the temperature. We have learned that substance around us change state from solid to liquid and from liquid to gas on application of heat. But here some facts noted that in below. Kelvin is the SI unit of temperature. 0 degree Celsius equal to 273.15 Kelvin. For convenience, we take 0 degree Celsius equal to 273 Kelvin after rounding off the decimal. To change a temperature on the Kelvin scale to the Celsius scale, you have to subtract 273 from the given temperature, and to convert a temperature on the Celsius scale to the Kelvin scale, you have to add 273 to the given temperature. Next are some that change directly from solid state to gaseous state and vice versa without changing into the liquid state. Some that change directly from solid state to gaseous state and vice versa without changing into the liquid state. Okay, here is activity 1.13. Take some camphor, crush it and put it in a china dish. Second, put an inverted funnel over the china dish. Next, put a cotton plug on the stem of the funnel as shown figure 1.7. Just like here, cotton plug, inverted funnel, camphor solidify, camphor vapors, china dish, okay, bottom burner, okay. Sublimation of camphor. Now heat slowly and observe. What do you infer from the above activity? A change of state directly from solid to gas without changing into liquid state is called sublimation, and the direct change of gas to solid without changing into liquid is called deposition. A change of state directly from solid to gas without changing into liquid state is called sublimation, and the direct change of gas to solid without changing into liquid is called deposition. Effect of change of pressure. We have already learned that the difference in various states of matter is due to the difference in the distance between the constituent particles. What will happen when we start putting pressure and compress a gas? Then, enclosed in a cylinder, will the particles come closer? What? Do you think that increasing or decreasing the pressure can change the state of matter? Here, figure 1.8, by applying pressure, particles of matter can be brought close together. Okay. Applying pressure and reducing temperature can liquefy gases. Applying pressure and reducing temperature can liquefy gases. Okay. Applying pressure and reducing temperature can liquefy gases. Mind it, it is most important. Yes. Have you heard of solid carbon dioxide, CO2? It is stored under high pressure. Solid carbon dioxide gets converted directly into gaseous state on decrease of pressure to 1 atmosphere without coming into liquid state. This is the reason that solid carbon dioxide is also known as dry ice. It is carbon dioxide gas. It is stored under high pressure. Solid carbon dioxide gets converted directly into gaseous state on decrease of pressure to 1 atmosphere without coming into liquid state. This is the reason that solid carbon dioxide is also known as dry ice. Got it? Thus, we can say that pressure and temperature determine the state of a substance. We can say that pressure and temperature determine the state of a substance, whether it will be solid, liquid or gaseous. Here, figure 1.9, interconversion of the three states of matter, solid, liquid and gaseous. Solid converted into liquid, liquid converted into solid. When solid converted into liquid, then fusion. Liquid converted into solid, solidification. Similarly, liquid converted into gas is called vaporization. Similarly, gas converted into liquid is called condensation, and solid converted into gas is called sublimation, and gas converted into directly solid is called deposition. Here is a solid, liquid and gas interconversion of the three states of matter. Atmosphere. ATM is a unit of measuring pressure exerted by a gas. The unit of pressure is Pascal PA. 1 atmosphere equal to 1.01 into 10 to the power 5 PA. The pressure of air in atmosphere is called atmospheric pressure. The atmospheric pressure at sea level is 1 atmosphere and is taken as the normal atmospheric pressure. Evaporation in 1.5. Do we always need to heat or change pressure for changing the state of matter? Can you quote some examples from everyday life where change of state from liquid to vapor takes place without the liquid reaching the boiling point? Water, when left uncovered, slowly changes into vapor. Wet clothes dry up. What happens to water in the above two examples? Okay. We know that particles of matter are always moving and are never at rest. At a given temperature in any gas, liquid or solid, there are particles with different amounts of kinetic energy. In the case of liquid, a small fraction of particles at the surface having higher kinetic energy is able to break away from the force of attraction of other particles and gets converted into vapor. This phenomenon of change of liquid into vapors at any temperature below its boiling point is called evaporation. Phenomenon of change of liquid into vapors at any temperature below its boiling point is called evaporation. Here, factors affecting evaporation. Let us understand this with an activity. Take 5 ml of water in a test tube and keep it near a window or under a fan. Second, take 5 ml of water in an open china dish and keep it near a window or under a fan. Okay. Take 5 ml of water in an open china dish and keep it inside a cupboard or on a shelf in your class. Record the room temperature. Record the time or days taken for the evaporation process in the above cases. Okay. Repeat the above 3 steps of activity on a rainy day and record your observation. Okay. What do you infer about the effect of temperature, surface area and wind velocity speed on evaporation? Yes. You must have observed that the rate of evaporation increases with first an increase of surface area. Of course, we know that evaporation is a surface phenomena If the surface area is increased, the rate of evaporation increases. If the surface area is increased, the rate of evaporation increases. For example, while putting clothes for drying up, we spread them out. Next, an increase of temperature. With the increase of temperature, more number of particles get enough kinetic energy to go into the vapor state. Okay. A decrease in humidity. Humidity is the amount of water vapor present in air. Humidity is the amount of water vapor present in air. Okay. The air around us cannot hold more than a definite amount of water vapor at a given temperature. If the amount of water in air is already high, the rate of evaporation decreases. Okay. An increase in wind speed. It is a common observation that clothes dry faster on a windy day. Yes, of course. With the increase in wind speed, the particles of water vapors move away with the wind, decreasing the amount of water vapors in surroundings. How does evaporation cause cooling? Question is, how does evaporation cause cooling? In an open vessel, the liquid keeps on evaporating. The particles of liquid absorb energy from the surroundings. They regain the energy lost during evaporation. This absorption of energy from the surroundings make the surrounding cold. Okay. What happens when you pour some acetone nail polish remover on your palm? Question is, what happens when you pour some acetone nail polish remover on your palm? The particles gain energy from your palm or surrounding and evaporate, causing the palm to feel cool. The particles gain energy from your palm or surroundings and evaporate, causing the palm to feel cool. Okay. After a hot sunny day, people sprinkle water on the roof or open ground because the large latent heat of vaporization of water helps to cool the hot surface. Can you cite some more examples from daily life where we can feel the effect on cooling due to evaporation? Question is, why should we wear cotton clothes in summer? Yes. During summer, we perspire more because of the mechanism of our body which keeps us cool. We know that during evaporation, the particles at the surface of the liquid gain energy from the surroundings or body surface and change into vapor. Okay. The heat energy equal to the latent heat of vaporization is absorbed from the body, leaving the body cool. Cotton, being a good absorber of water, helps in absorbing the sweat and exposing it to the atmosphere for easy evaporation. Okay. The heat energy equal to the latent heat of the vaporization is absorbed from the body, leaving the body cool. Cotton, being a good absorber of water, helps in absorbing the sweat and exposing it to the atmosphere for easy evaporation. Question is, why do we see water droplets on the outer surface of a glass containing ice cold water? Okay. Let us take some ice cold water in a tumbler. Soon we will see water droplets on the outer surface of the tumbler. Yes, of course. The water vapor present in air on coming in contact with the cold glass of water loses energy and gets converted to liquid state, which we see as a water droplets. The water vapor present in air on coming in contact with the cold glass of water loses energy and get converted to liquid state, which we see as water droplets. Here, what you have learned. First, matter is made up of small particles. The matter around us exists in three states: solid, liquid, and gases. Next, the forces of attraction between the particles are maximum in solid, intermediate in the liquid, and minimum in gases. Next, the spaces in between the constituents particles and kinetic energy of the particles are minimum in the case of solids, intermediate in liquids, and maximum in gases. Next, the arrangement of particles is most ordered in the case of solids. In the case of liquid, layers of particles can slip and slide over each other, while for gases there is no order. Particles just move about randomly. Next, the states of matter are interconvertible. The state of matter can be changed by changing temperature or pressure. Sublimation is the change of solid state directly to gaseous state without going through liquid state. Next, deposition is the change of gaseous state directly to solid state without going through liquid state. Okay. Boiling is a bulk phenomena. Boiling is a bulk phenomena. Particles from the bulk hole of the liquid change into vapor state. Next, evaporation is a surface phenomena. Particles from the surface gain enough energy to overcome the forces of attraction present in the liquid and change into the vapor state. Next, the rate of evaporation depends upon the surface area exposed to the atmosphere, the temperature, the humidity, and the wind speed. Okay. Evaporation causes cooling. Latent heat of vaporization is the heat energy required to change 1 kg of a liquid to a gas at atmospheric pressure at its boiling point. Okay. Latent heat of fusion is the amount of heat energy required to change 1 kg of solid into liquid at its melting point. Some measurable quantities and their units to remember: quantity, unit and symbol. Temperature Kelvin, symbol K. Length meter, symbol M. Mass kilogram, symbol kg. Weight Newton, symbol N. Volume cubic meter, symbol MQ. Density kilogram per cubic meter, symbol kg per meter cube. Pressure Pascal, PA. Here is end of session. No exercise is here. You can go through it. Okay. Here is group activity. Okay. So I am stop this video. Thank you for watching this video. Thank you so much. I hope this video is important for everyone. Thank you so much.